also have to be cognizant that we're not going too fast during these moves. And one example to look at there would be this microtiter plate, which had 4.5 millimeters between wells. So if we take, call the equation that V max is equal to 2x over t, also equal to the square root of x times a. If we take that move distance of 0.0045 meters, and let's say we wanted to operate at 3 Gs, or 30 meters per second squared, that is a peak velocity of 365 millimeters per second, or 0.365 meters per second. That's a pretty good clip. Remember, we're only going from one of these to the next one, very short distance, and yet we've hit a peak velocity that's over 1/3 of a meter per second. So as you go to longer moves, that velocity might easily exceed some limitations of your system that could be either in the encoder or in the motor and bus. So the bus voltage is important because motors have what's called a back EMF constant. And so the faster they go, the more back EMF they produce. And there's a point at which, for a given bus voltage, you can't go any faster. You're going to begin to saturate your loop. So there's a variety of things you have to be careful there. There's another quality factor that can be described for linear motor systems, and that is the factor K sub s. And what K sub s amounts to is linear motors have something that we want from them, which is acceleration, and they have something that we just as soon not have, which is waste heat. Because ultimately, if the motor temperature gets to a certain threshold, you can't hit it any harder. Now, if the coils were superconducting, we wouldn't have that kind of problem. Their resistance would be 0, but they do have a resistance, and I squared R is the power, and so this does set a practical limit. So K sub s is a quality factor for a stage, and it is the mass squared divided by K sub m squared. And this quality factor, which, by the way, this mass is not only the payload mass, but it's the stage moving mass. So for example, if you have a stage with a modest K sub m, but the stage is very massive, it's going to have a low value of K sub s. And it's going to do a bad job of giving you what you want, which is acceleration, and not giving you what you don't want, which is the waste heat. Commensurately, if you go with a very lightweight stage, and your payload is lightweight, and then you couple that with a very high K sub m motor, now you're going to be able to do very high accelerations without incurring a lot of waste heat. However, there are limitations to how much acceleration you can use. In this graph, the vertical axis is the move time in seconds. The horizontal axis is acceleration in meters per second squared. And the various color plots, starting at the bottom red, that's a move of 0.5 millimeter. The dotted blue is 1 millimeter. The dashed green is 2.5, and the dashed purple is 5 millimeters. So clearly, as you increase acceleration in the beginning, your move time drops a lot. The more the move time drops, the higher the throughput, the higher the productivity. That's all good. But you'll notice that all these curves have a kind of similar tendency, which is that as you get the acceleration higher and higher, you reach diminishing returns. Now remember, the heat, the waste heat, is going to go up as the square of that acceleration. So it is not free by any means, but it's not doing a lot of good for us in getting that move time down. So generally speaking, there's a sweet spot where you would like to operate. Now, if we go back and look at a typical move profile, and again, we prefer to do it in terms of velocity versus time. In a normal servo system, during the acceleration phase, the payload and the stage will lag the command. So it's really, now this is actually in position space, so it's a little awkward, but I think this makes it pretty clear. It is lagging during accel, and it is leading during decel. And the reason is simple, that the proportional term of the servo is such that without an error, you don't get a response. And so it takes this error to generate the response. So it always lags during accel and leads during decel. And that means that at the moment of trajectory completion, which is here, our stage is not where it wants to be, but it is, and again, apologies, this is mixing a bit of position and velocity commentary, but it is past where we want it to be. And that terminal following error, or the following error at the moment of trajectory complete, is simply 4 times the acceleration divided by omega 0 squared, where omega 0 is 2 pi f sub 0, where f sub 0 is the servo bandwidth. This is a very important parameter of servo systems, and there's alternate descriptions of how to measure it, but typically it is when for small signal, there is a 90-degree phase relationship, phase lag between the excitation and the response. And so that's the beginning of the point where the response of the system, as you amplitude versus frequency, it starts out flat, depending upon the damping, picks up a little bit, and then drops off. So the minus 3 dB down point is another way to look at it, but we generally prefer a 90-degree phase relationship between excitation and response. And the job of the servo loop is then to take this terminal following error, which we've calculated here, and obviously having the servo bandwidth higher is going to help a lot. Lowering the acceleration helps, but that was the whole point, to get there fast. But again, as we saw, too much acceleration doesn't always help. So this is the residual error that will have to settle, because remember, our mission is move very fast and hold really still. And from the moment that the trajectory is complete to the point where we are actually holding really still, that we call the settling time. Now, there are a variety of tools that we can use to improve the settling time. One of those is to use something called acceleration feed forward. And acceleration feed forward says, I'm about to provide an acceleration and I know it's going to lag. Why don't I give it some additional acceleration and kind of try to push this curve back that way? And during decel, the same thing. So the acceleration, which is during this half, and the deceleration during this half, we're going to put a little extra on those and try to pull these back to where they belong. And acceleration feed forward is a fantastic tool. If you use it, you can reduce the terminal following error and shorten the settling time. And the nice thing about acceleration feed forward is that it is a feed forward. And as a result, it does not upset the servo dynamics. If you try to do this by adjusting the servo bandwidth, you could run into trouble. That is true feedback. But in this case, it's feed forward, and it will not disturb the stability of the system. Now, as you increase the acceleration feed forward, things get better and better and better, and this gets smaller and smaller and smaller. And then if you put in too much, it begins to go the other direction. And then you know to back off and put it at that sweet spot right in the middle. Another thing that you can do is to stop using a triangular profile. And that is to go to an S-curve. So in S-curve, in the previous drawing, the acceleration, you may recall, was a square wave. It was immediately turned on for the accel phase, and then flip sign, but immediately it's basically a square wave. When you use S-curve, either partial, where the acceleration is shown up here. So the velocity now looks rounded rather than triangular, but the acceleration is ramped in from 0 up to its peak and held constant. and then again it reverses for the deceleration phase. But when we use full S-curve, the acceleration is triangular. And what's really interesting about this is that the acceleration peaks here and here. Now, this point is long before the end of the move. But this point is not that long before the end of the move. And what's very interesting is at the end of the move, the acceleration is 0. And therefore, the lag is 0. So S-curve, full S especially, is really, really helpful because the disturbance that's going to create the following error isn't there anymore. It happened a while ago here, and it gets to decay. So full S-curve really helps to improve settling. So an alternative that's a little better yet is that instead of doing a triangular acceleration profile, we use a sinusoidal acceleration profile. Now, when we look at velocity versus time here, it looks pretty much like an S-curve. Really hard to tell the difference. But the acceleration curve is where it really stands out. Instead of a triangle, it's now a sine wave. And the next derivative, jerk, which was infinite at the beginning and turnaround points of a S-curve, when the triangular acceleration, the jerk is also cosine in that case. And the same thing occurs for all higher derivatives. Not that anybody seems to pay too much attention of anything beyond jerk. Let's recall the difference. S-curve had a triangular acceleration profile. Triangular velocity had a square wave acceleration profile. And one thing that we can speak about is that from basic Fourier theory, I think people know that when you hit a square wave with an instantaneous step, if you look at the spectral content of that, it's got a lot of spectral content going out to many, many, many orders. So there is a lot of high frequency stimulus to the system when you employ a triangular move profile. When you use a triangular acceleration profile, that is to say S-curve, you're doing better, but triangles have harmonics as well. Whereas when you have a sinusoidal acceleration, there are no harmonics of that. All you get is the fundamental. So there are not these higher frequencies that are exciting your structure and potentially causing problems in tuning your system. So when you can, even better to use a sinusoidal acceleration profile. While we're not about to go into all of the hoary details in this video, we have an upcoming white paper that goes into a lot more detail on sequential field imaging. There's also going to be another on TDI scanning imaging, but it would be helpful to just briefly show a table. Here we have the 3 different types of motion profile: triangular, full S, and sine acceleration. Very interesting thing to note, which is that the peak velocity that those 3 very different trajectories generate are all calculated by the same exact very simple formula. 2 times the move distance divided by the move time gives you the peak velocity. Now, the peak accelerations vary. We covered 4x over t squared earlier. They differ for the others. So do the harmonics. There are none in sine acceleration. This is formula for decel. The power that the move uses changes. The move time compared to that of a triangular velocity profile changes. And the jerk goes from infinite to these 2 values for, again, the 3 different profiles.